Hello everyone, welcome to my class. In today's class I am going to cover change of variables in multiple integrals. So let me start the class right away. First, let me recall the substitution technique that we learned in Calculus 1. In Calculus 1, to integrate a complicated integral in x variables, we use the substitutions where we put x equals to function of u, and then we convert the x integrals to the u integrals. The whole purpose of converting the x integrals to u integral is simpler than the x integrals to evaluate. So quick example, let's evaluate the integral of x times sine of x square, x equals to 2 to 3. So solutions, put x equals to function of u. So here x square equals to u, then take its derivative. Then it turns out that after simplifying this expression here, we have x times dx equals to 1/2 du. Also change the limits of integrations. So here when x equals to 2, u equals to 4. When x equals to 3, u equals to 9. Then our x integrals reduces to the u integrals here. Here sine of x squared becomes sine of u, and x times dx equals to 1/2 du, and we have the new limits for integrations. The u equals to 4 to 9. So now comparing these two integrals, this u integrals, integrals in terms of u variable, is simpler to evaluate than the given x integral. So now here we can easily evaluate this u integral. Let me scroll down. Yeah. So the integration of sine u is negative cosine u, 1/2 as it is. Then put the u limits, u equals to 4 to 9. Then simplifying, it gives us the value of this given integral equals to 1/2 times cosine of 4 minus cosine of 9. Great. So now in Calculus 3, we used to perform a similar substitutions for multivariable integrals. A change of variables can be useful in evaluating the double and triple integrals. So first, let me define the Jacobian of a transformations. For function of two variables, here f is a function of x and y, let x equals to function of uv and y equals to function of ub be a transformations of the plane. Then Jacobian of the transformations is defined and denoted by j. This equals to the ratio of these partial derivatives. It's the del xy over del uv. Then this Jacobian equals to the determinant of this 2 by 2 matrix. So where these entries are just the partial derivatives here. The entries are the partial derivative of x with respect to u, the partial derivative of x with respect to v, and here in the second row, the partial derivatives of y with respect to u, and the partial derivatives of y with respect to v. This is simply the 2 by 2 determinant. Similarly, for function of three variables, we have the Jacobian j equals to the 3 by 3 determinants whose entries are in the first row xu, xv, xw, second row yu, yv, yw, and third row gu, gv, gw. Just like this one, but here we have 3 by 3 determinant. Great. I hope this definition makes sense to you all. So quick side notes. The area element in the new region UB plane is dA equals to dx dy equals to the magnitude of the Jacobian times du dv. Similarly, the volume element in the new regions UVW plane is Jacobians, that the absolute value of Jacobian, times du times dv times dw. Great. So next, let's talk about change of variables in double integral. So Here is a change of variables in double integral template. Suppose T is a transformations whose Jacobian is non-zero, and the transformations T maps a region S in UV plane onto a region R in the XY plane by means of these equations. X equals to function of UV, Y equals to function of UV, then the double integrals of F over R turns out to be the double integrals over the new region S, F of X, Y, where X and Y are function of UV, times the absolute value of Jacobian of these transformations times du dv, and here the image of S equals to R. Since our transformation is 1-to-1, so it's invertible, so then T inverse R equals to S. Some special examples. Let's find the Jacobian of the transformations from Cartesian's coordinate to the polar coordinates. So we define the transformations by putting x equals to r cosine theta and y equals to r sine theta in polar form. Let's compute the Jacobian of these transformations. So the Jacobian equals to the ratio of these partial derivatives. So the Jacobian equals to the 2/2 determinant of those partial derivatives. Here the partial derivative of x with respect to r, partial derivative of x with respect to theta, partial derivative of y with respect to r, and partial derivative of y with respect to theta. And in the next step here, so xr turns out to be cosine theta. Next, x theta turns out to be negative r sine theta. Here r is constant for theta partial derivatives. Similarly, in the second row, we have sine theta, r cosine theta. We expand this determinant, we multiply this diagonally, and we multiply this diagonally, and we subtract the product along this diagonal entries from the product along these diagonal entries. So we have r times cosine square theta minus r sine square theta. That is, we have r cosine square theta plus r sine square theta. Then we pull the r outside, then inside the parenthesis we have cosine square theta plus sine square theta, which turns out to be 1. So we have simply r. Area element, the dx dy in xy plane, and in the r theta plane the area element is r times dr d theta. This r is the absolute value of Jacobian of the transformations. I hope this idea makes sense to you all. Now let's move on. Next example, let's compute the Jacobian of the transformations from Cartesians to cylindrical, and we define the transformation by these equations: x equals to r cosine theta, y equals to r sine theta, and z equals to z. Jacobian j equals to this 3/3 determinant. The first row is xr, x theta, xz. Second row is yr, y theta, yz. And third row is zr, z theta, zz. Next step, these are the partial derivatives. Accordingly, we computed. Then after expanding this 3/3 determinants, we will get r. Now our Jacobian equals to r. Hence in the volume element, dv turns out to be again r dr d theta dz. We were familiar with this form in cylindrical triple integrals, where we substitute dv equals to r times dr times d theta times dz. Awesome. Let's move on. Let's compute the Jacobian of the transformations from Cartesians to spherical. We define the transformations by putting these equations here: x equals to rho cosine theta sine phi, y equals to rho sine theta sine phi, and z equals to rho cosine phi. Then the Jacobian equals to again this 3 by 3 determinant of those partial derivatives. These are the corresponding partial derivatives, and after expanding these 3 by 3 determinants, we will get Jacobian equals to rho square sine phi. Awesome. Similarly, the volume element in spherical coordinate dv turns out to be the rho square sine phi times d rho times d phi times d theta. Great. So now this mysterious term rho square sine phi in our spherical triple integrals in the volume element, now this is simply the Jacobian of the transformations. Awesome. Let's move on. Quick remark. If a transformation is not given, then the first step is to think of an appropriate change of variables. In such cases, the form of the given functions may suggest a transformations. Now, let's do some example. Example first. Suppose a region R in xy plane is bounded by the circles x square plus y square equals to 1 and x square plus y square equals 2 in first quadrant. Find equations for A transformations that maps a region S in UV plane onto R in xy plane. So let's begin the solutions. First, let's sketch the region R in xy plane. So here, this is a unit circle. This is the circle of radius radical 2. Since the region R lies in the first quadrant, so this shaded part is the regions here given to us. So now it's an annular region, so in polar descriptions, R equals to set of all order pair R theta, where R lies between 1 and radical 2 and theta between 0 degree to pi half. So this description is simply this shaded region. I hope this makes sense to you all. So now this gives us an idea. Now we need to find a region in UV plane. So now we are finding a region in R theta plane. So let's define the transformations in this way. X equals to u cosine v and y equals to u sine v. So here in polar representations, x equals to r cosine theta, we are putting r equals to u and theta equals to v. Similarly, in y equals to r sine theta, we are putting r equals to u and theta equals to v. So these are the polar forms. So then the new region in UV plane is described by this order pair uv, where u lies between 1 and radical 2 and v lies between 0 and pi half. And this new region S in UV plane is simply a rectangular region. Let me show you here. Let me visualize here. So this R is the region given to us, and we define a transformations, and we found a new region in UV plane such that the image of this new region under this transformation T is R. I hope this idea makes sense to you all. Great. Now let's move on. Now let's do example 2. Use the given transformations. Here the equations are x equals to 2u and y equals to 3v. To evaluate the double integral is given to us double integral of x square over r, where r is the region bounded by the ellipse in xy plane. This is the equation of ellipse. So let's begin the solutions. So the idea here is we need to find out the Jacobian and the corresponding region in the UV plane such that the image of this new region under the transformations is the ellipse, and we are integrating the double integral over the new region in UV plane instead of over ellipse. So first let's find the Jacobian. By formula, this Jacobian equals to the 2 by 2 determinants whose entries are here xu, xv, yu, yv. So here xu is 2, xv is 0, yu 0, yv 3. Then expand this 2 by 2 determinant, multiply this diagonally, 2 times 3 is 6, multiply this diagonally, 0 times 0 is 0, so 6 minus 0 is 6. So we found the Jacobian 6. Now, under the given transformations, the new region S in UV plane is obtained by solving the equations here. So this is the equation of ellipse. Let's put x equals to 2u, y equals to 3v, and simplify. This gives us u squared plus b squared equals to 1. That's a unit circle. So that means we found a new region in UV plane, which is a unit circle, whose image under these transformations is the ellipse, this given ellipse. So hence, given double integrals here, I equals to the double integrals of x squared over r, and we are integrating with respect to dA, equals to, since x equals to 2u, so 2u squared is 4u squared, and then integrating over the new region S in UV plane, and then here multiply by the Jacobian's absolute value. So this is the absolute value of Jacobian. The Jacobian is 6, by the way, is positive, times du times dv. I hope this setup makes sense to you all. Then the next step here, so I put the Jacobian is 6, since S is u squared plus b squared equals to 1, 6 times 4 is 24, u squared du dv. I hope this makes sense to you all. So now we are integrating of 24u squared over this unit circle. Since our domain of integration is circular, we use a polar form. Let's put u equals to r cosine theta, v equals to r sine theta, where r between 0 and 1 and theta between 0 and 2 pi, and du dv equals to r times dr d theta. So hence, from this step to here, let me go this way. So double integrals, this is theta integral, this is r integrals. R goes from 0 to 1, theta from 0 to 2 pi. The integrand function is 24 as it is. Since u equals to r cosine theta, so here r is square cosine square theta, which is u square, by the way, times du dv is r dr d theta, r dr d theta. I hope this conversion makes sense to you all. Then the next step, 24 constant as it is. Let's isolate the r integral and theta integrals. Now from r integrals, so here I do have r cubed, so the integration of r cubed is r4 over 4, and these are the r limits, times theta integral 0 to 2 pi cosine square theta. Cosine square theta becomes 1 plus cosine 2 theta over 2 times d theta. The next step, put r equals to upper limit 1 and lower limit 0 and simplify. It gives us simply 24 times 1 over 4, and let's cancel this 24 by 4 6 times, and this 6 cancel by 2 3 times, so we have 3. Then from the theta integrals, here's 1 becomes theta, and cosine 2 theta becomes sine 2 theta over 2. These are the theta limits. Simplify these last expressions, then this gives us 6 pi. Hence, we found the value of this given double integrals is 6 pi. I hope this computation makes sense to you all. Great. Now let's move on. Example 3. Awesome. So example 3, evaluate the double integrals of this ratio. So here our function is given in the ratio, in the fraction form, x minus 2y over 3x minus y. The integrations is over r, where r is the parallelogram enclosed by the lines. Lines are x minus 2y equals 0, x minus 2y equals 4, 3x minus y equals 1, 3x minus y equals 8. by making an appropriate change of variables. So here our first step is to find the transformations, and then find the Jacobian of that transformations and use the formula. So first, let's put u equals to x minus 2y, v equals to 3x minus y. Since we have not given the transformations here, so the function suggests us a transformations. So to define a transformations, we put u equals to x minus 2y and v equals to 3x minus y from these functions here. You can switch this here. That means you can put u equals to 3x minus y and v equals to x minus 2y. It doesn't matter. Great. So with this substitution, these equations define a T-inverse transformations from xy plane to uv plane, but we need the transformations from uv plane to xy plane. So let's solve these equations for x and y. So after solving, we got x equals to 1/5 times 2v minus u, and y equals to 1/5 times v minus 3u. Now these x and y equations defines a transformations T that we are looking for. Next, let's find the Jacobian of this transformations T. So here J equals to the determinant of 2 by 2 matrix here, whose entries are xu, xv, yu, yv. So from these equations here, the xu turns out to be negative 1/5, xv turns out to be 2/5. Similarly, yu turns out to be negative 3/5, and yv turns out to be 1/5. Simplify this determinant, expand this determinant, it gives us the Jacobian equals to 1/5. And by the way, since we substitute u equals to x minus 2y, so the ranges of u's are 0 to 4. And similarly, since v equals to 3x minus y, from these equations, v ranges from 1 to 8. I hope these limits make sense to you all. So here, hence under the above transformations, according to these equations, the new region S in uv plane is enclosed by set of all order pair uv such that u lies between 0 to 4 and v lies from 1 to 8. So let me visualize those regions here. Here is a new region S in uv plane where these u, these are the vertical lines, and v the horizontal lines. So u lies between 0 to 4 and v between 1 to 8. And under the transformations T defined by those equations here, we have this image of S is in the xy plane, which is R. By the way, this R is the region given to us. R is the parallelogram enclosed by the given lines here, which is here. So here this U corresponds to this, I distinguish by this color, red to red, and this blue lines, these are the V lines. Now here these are the corresponding V values in terms of x and y. I hope this makes sense to you all. So now instead of integrating over this region in xy plane, we integrate over the S region in uv plane. S region looks simpler than the R regions. Let me scroll down. Hence, the given integrals, the double integrals of x minus 2y over 3x minus y over R becomes here the double integrals over new region S. X minus 2y is u, 3x minus y is v. That's what we substitute here. Then we multiply by the absolute value of Jacobian times du dv. The next step, the integrand function is u over v, and Jacobian is 1/5 that we computed here. That's the Jacobians times du dv. And in this order of integrations, inner integral is our u integrals, outer integral is our v integrals. But here both limits are constant, so order doesn't matter. We can isolate the integrals when you evaluate this double integral. So v limits are 1 to 8, u limits are 0 to 4. Here, u 0 to 4, v 1 to 8. Then next, let's isolate the u integral and v integrals. So here, 1/5 as it is. This is u integral, this is v integrals. In the next step, 1/5 as it is. So u integrals is u square over 2. These are the u limits times the integration of 1 over v with respect to dv becomes ln v from 1 to 8. And now put the upper limit, put the lower limit, and simplify these last expressions. It turns out that the double integral's value equals to 8 over 5th times natural log of 8. Great. So I hope this idea makes sense to you all. Now we finish this change of variables in double integrals. Similarly, we finish the chapter 15, and in next class we will start chapter 16. Thank you.